Many biological systems rely on the physical properties of fluids to ensure proper function, one of which is the vascular system of plants, particularly the flow of water through xylem tissue to maintain vital gas exchange. In vascular plants, constant water flow through the xylem must be maintained to facilitate sufficient gas exchange. Water evaporates from the top of the plant through small pores in its leaves, and water is drawn into the plant through the roots. This creates a pressure gradient from high pressure in the roots to low pressure at the tip of the plant. This gradient causes water to flow through the plant from roots to leaves at a steady rate, as long as the loss of water through leaves and the gain of water through the roots is maintained. We can easily apply the principles of fluid dynamics to a model plant system, which we will now demonstrate. A 3-meter tall plant needs to have water flowing through it at a rate of 0.43 meters cubed per second to maintain a safe level of gas exchange. The pressure in the roots of the plant is 1.7 times greater than the pressure at the tip of the plant where water evaporates from. Assume that the plant is a perfect cylinder of diameter 2 centimeters. What is the pressure in the roots?
We can begin by identifying the values we have been given and using them to create a diagram that will help us solve this problem. We are told that this plant is a perfect cylinder of height 3 meters with a diameter of 2 centimeters. It also has a root pressure that is 1.7 times greater than the pressure at the tip of the plant. We are also told that the rate of flow through this plant is 0.43 meters cubed per second. We can apply Bernoulli's equation for water flow in this situation, which is stated as follows. Let's take our 2 points for the equation to be right at the root and right at the tip of the plant. So our equation becomes Since we're dealing with a perfect cylinder, the cross-sectional area does not change, and thus by the continuity equation, neither does the flow rate. So this means that the kinetic energy terms are equal, and they can be cancelled out from our equation. We can begin by subtracting this term from both sides. We can now factor out PR. Now we can divide this term on each side. This is our final equation, and we know the values of these two. So we can take raw water to be 997 kilograms per meters cubed, and we can take the acceleration due to gravity to be 9.81 meters per second squared. Now let's plug in these values. Now this number comes out to be 71,258.4395894, and this is in units newtons per meter squared, which is equal to 0.001 kilopascals. So if we divide this answer by 1,000, we will have our final answer in terms of kilopascals, which turns out to be 71.258 kilopascals.